Welcome back. We've looked at transverse standing waves, and now it's time to look at longitudinal standing waves, which are mostly the same with a few important differences. And we will also look at their applications to musical instruments. That's kind of the point of talking about standing waves in sound, so that we can talk about these familiar things: trumpets, saxophones, the human voice. And you might be glad to hear that there's very little math in this presentation, mostly pictures, beginning with these. So the first thing you should understand about this picture, and you'll see many pictures like it, is that it's schematic. In the previous part of the chapter, when we were talking about standing waves on strings, these little cartoon pictures actually showed you the profile of the string. If you were to look at the string from the side, freeze time, a so-called snapshot graph, the graph really is the shape of the string. It's very different for longitudinal waves, though, because the thing that's waving, or the things that's waving, that are waving, are the particles. They're wiggling back and forth, not transverse. They're wiggling back and forth in the same direction that the energy is sloshing back and forth. So we have to represent their displacement schematically with the height of a curve that's transverse. So there's that little abstract step that you have to make in order to understand the meaning of these pictures. Down here, we've got a graph I pulled off the web of the various standing waves which may exist simultaneously inside a trumpet, because remember, a trumpet is a column of air and it can support several different standing waves at the same time. That's the principle of superposition. Once those standing waves produce progressive waves which leave the bell of the trumpet and radiate outwards, some of those waves might enter your ear canal. And we've already looked briefly at the fact that even your ear canal, which is a column of air, responds preferentially to some frequencies over others. And the condition for that preference is something that we'll look at in just a moment. And here's one of the awesome simulations from Dan Russell's website. And honestly, these are going to make up about half of this presentation. They're so awesome. They kind of replace the need for a lot of verbosity. There's a lot of words we don't need. We can just look at the picture. Here's a reminder of what progressive, also known as traveling, longitudinal waves look like. We say traveling because the wave fronts themselves really do travel from one end of the tube to the other. That's not to say that the particles themselves are moving from one end of the tube to the other. So when we say traveling, we don't mean the particles are traveling, it's the energy that's traveling from one end to the other. And again, if you focus your attention on the particle that's been highlighted in red, that makes it very clear that it's really just wiggling back and forth about its equilibrium position. So at any point in time, it has a displacement to the right or to the left. That axis of displacement is parallel to the direction that the energy flows, hence the name longitudinal wave. Now we can move on over to an animation of standing longitudinal waves, and the behavior is immediately different. In this case, we don't actually see wave fronts traveling from one end to the other. We see regions of large amplitude oscillations, regions of low amplitude oscillations. So right here, hopefully you can see my mouse pointer, centered on this red particle. The particles that line up vertically with that one, they have very small or zero amplitude of oscillation. And that position of zero amplitude oscillation stands in place, standing wave. Whereas the regions with large amplitudes of oscillation, it looks like he's got this other dot highlighted in red. That vertical location of particles with large amplitude oscillations also stands in place. So there's the meaning of the word, or of the term, standing wave. Now there's a whole bunch of observations we can make just from this animation. First, let's talk about the displacements of the particles in relation to boundary conditions. So we go over here to the right end, and you'll notice these particles are not free to jiggle back and forth because they bump up against the closed end of the tube. So they're prevented from having any amplitude of oscillation. That's the boundary condition. As a result, we call that a displacement node. As you see on the graph here, the right end of the graph is a node. So the vertical up and down motion in this animated plot actually represents the side-to-side displacement of the particles. Obviously, we can't make a graph where the curve, each point on the curve wiggles left and right, because you wouldn't see anything. It would still be a flat line. So we have to use up and down motions of the curve to represent side-to-side wiggles of the particles. So that's fact number one. For a closed end of a tube, when you're talking about standing longitudinal waves, the closed end must be a displacement node. That's the boundary condition. The particles are not free to wiggle back and forth there. But you might notice that every half period, the pressure or the density, they're related. The pressure goes up. Right now it's high, right now it's low. High, low. So the pressure is fluctuating with maximum amplitude at the end of the tube. The particles get bunched up or compressed and they get rarefied. And that's what we see down here. So this is a graph of the, and I should really say the differential pressure, because if there were no wave in the tube and it was open to the atmosphere, the pressure throughout the tube would be atmospheric pressure, 100,000 pascals. So this pressure that we're looking at in time is really a fluctuation about that atmospheric pressure, or you could call it differential pressure. If we focus our attention again on this second red dot, again, that's a vertical. If we look at all the particles lined up vertically, they all have a maximum amplitude of displacement in time. So that is a displacement antinode, as you can see in the plot directly below. You'll also notice, if you continue down vertically, that a displacement antinode corresponds to a pressure node. And that's less obvious than my previous observation. When I look at the region here that's sloshing back and forth with greatest amplitude, it's not particularly obvious that there's no fluctuation in pressure. I guess if you really pay attention, you'll notice that the density within that region doesn't seem to be changing in time. It's not like the particles are getting more squished together and then more rarefied. Over here, they definitely are. You can see them squishing together, spreading apart, squishing together. Over here, not so much. So that's the second fact that you want to know. Anytime or any place where there's a displacement antinode, where the particles jiggle back and forth with the greatest amplitude, that is a pressure node. But the wavelength doesn't change. You see that? If you go from one displacement node to another displacement node, half a wavelength away, that distance is the same as the distance down here from one pressure node to the next pressure node. Pardon me. What else can we say about this animation? Well, this little piston that he's put in the animation might be a little misleading. Try to remove it from your mental picture here, and then you would see that those particles are open to the atmosphere. Actually, that's not even necessary. What you could do is use Newton's second law. Let's pretend that this piston on the left side here is massless. And if you've taken mechanics with me, you know that anything that's massless has to have a net force on it of 0 at all times, because in F equals ma, if you had a tiny mass with any force on it, you would have an extremely large acceleration. So let's just make the assumption that there's no net force on this massless piston. And that means that the air inside the tube pushing to the left, so all of this air is squishing back and forth, pushing to the left on the piston, has to push just as hard as the atmosphere outside pushes in. In other words, the pressures must be the same. So the pressure just inside this piston, where the particles within the tube are jiggling back and forth, that pressure must always match the pressure outside, and the pressure outside doesn't change because it's atmospheric pressure. So you just make the assumption that just on the other side of the piston, inside the tube, that pressure must match atmospheric pressure. And when it comes to musical instruments, you don't even have to worry about that, because a trumpet, for instance, is open at the bell end. It is open to the atmosphere. All right, so that's I guess the third observation we'll make about this simulation here. Also, you can see, because these particles don't have their density changing in time, they're not getting more or less squished together. That has to be a pressure node. Sure enough, we look down at the bottom graph, the end that's, I'm going to say, quote, open to the atmosphere. Again, the simulation has a piston here, but let's forget about that. The end that's open to the atmosphere has no fluctuation in pressure because it must match the atmospheric pressure. That's the pressure boundary condition. I think that's all we need to say about this particular simulation. What do we have down here? And I do encourage you to read the background information here. Okay, here are the first 4 modes, and the author here has chosen to name them the first harmonic, the third harmonic, the fifth harmonic, and the 7th. Those are odd integers, 1, 3, 5, 7. We will explain that later in the presentation. Right now, let's just look at the behavior. So what do we have going on here? The top graph up here is of displacement versus time. We know that the right end is closed. It must be a displacement node. And we know that if we go over to the left end, the boundary condition there is that the pressure must match the atmospheric pressure at all times. In other words, there's no fluctuation. That would be a pressure node. And a pressure node corresponds to a displacement antinode. So I guess what you do is you apply one boundary condition to locate the nodes of displacement, and you apply the other boundary condition to locate the nodes of pressure. If the end is closed, that boundary condition requires that it be a displacement node. If the other end is open, that boundary condition requires that the pressure have a node right there. And then you just remember the rule. Pressure node is the same location as a displacement antinode, and a displacement node corresponds to a pressure antinode. That's it. And you should pause for a moment and ask yourself, how many wavelengths do I see in this tube? Because I don't even see one full hump. I like to say, sine has 2 humps, an up hump and a down hump. Same with cosine. How many humps do we see here? Because 2 humps make a wavelength. It looks like we only have half a hump. Well, 1 hump is half a wavelength, and we're looking at half a hump. So that must be 1/4 wavelength. So the fundamental mode for a pipe that's closed at one end and open at the other has a wave in it where the length of the tube equals 1/4 of a wavelength. Moving on to the second mode. Any differences that we immediately recognize? Well, the animation is showing that these particles are jiggling back and forth more quickly than the ones in the first mode. Hopefully that's clear. So we already know that the frequency is higher. Makes sense. When we looked at the allowable frequencies on a string, standing waves on a string, we found that all of the frequencies of the standing waves are higher and higher multiples of the fundamental frequencies. So it's not surprising that these next modes would have higher frequencies. Let's check our boundary conditions. We know that the closed end must be a displacement node, and it is. That would also be a pressure antinode, and it is, according to the graph. We know that the far left end, which is open to the atmosphere, must have a pressure node there. There's no fluctuation of the pressure around atmospheric pressure. Yes, the graph shows that there's a pressure node, and that tells us that there's a displacement antinode. So you may be thinking, do we have to jump from this picture to this picture? This first one had 1/4 of a wavelength. This one, if we count, I'm going to go from the right end, that's 1 hump, which is a half a wavelength. Or you could say 2/4 of a wavelength, right? One hump is half a wavelength, which is the same as 2/4. And then we have an extra quarter in there. So count them up. You've got 1, 2, 3/4 of a wavelength for this mode, and only 1/4 here. So if you're thinking, why did we skip the 2/4 of a wavelength mode? Why did we go straight from 1/4 to 3/4? Try it. Try to draw a mode on paper that's got 2/4 of a wavelength. In other words, half, right? 2/4 is a half of a wavelength. And what you'll find is you're not able to satisfy the boundary conditions. It's not possible to have a displacement node on the closed end and a displacement antinode on the open end with half a wavelength. So The allowable modes are a consequence of the boundary conditions. And I'm emphasizing that relation because it shows up all over the place in physics. When you look at the reflection and transmission of light at a boundary between two mediums like air and glass, you have to apply boundary conditions to Maxwell's equations to figure out how much of the light will be reflected, how much of it will be transmitted. Let's just quickly go through the next two modes. And maybe you see already why the author is calling this the third harmonic, because here we've got 1/4 of a wavelength. Here it's 3/4. That's third harmonic. And we will see that the frequency at which these particles oscillate is 3 times the frequency of the fundamental. Hence the name third harmonic. Okay, down here, again, enforce your boundary conditions. And the very next mode that you can draw has to skip from 3/4 of a wavelength to, let's count them. Well, every hump is 2/4. So we've got 2/4, another hump is 4/4, and then 1/4 of a wavelength after that. So this is 5/4 wavelengths. By the way, what we're talking about is often called an open-closed tube. Open-closed. Opened at the right end, whoops, closed at the right end, excuse me, and opened at the left end. And this basically is a lot of musical instruments, like the saxophone. The player's lips are sealed around the reed. That's the closed end. And then what do you call the end of a saxophone? Is that the bell? I don't know, but obviously the other end of the saxophone is open to the atmosphere. Sure, the tube is bent up and it's got valves and holes and all this other stuff, but topologically, I guess you could say, it's a lot like this. It's just like they say the human body is like a donut topologically. Kind of gross to think about, but I'll let you figure out what that means. Do I need to go through this last one? I think you can count. There are 7/4 wavelengths. So it may be the fourth mode, 1, 2, 3, 4, but you could also call it the 7th harmonic, because we're going to see that the frequency of oscillation here is 7 times what the fundamental is. So make sure you make that observation visually here. Each successive mode has particles oscillating more quickly. Here's a slightly different animation of longitudinal standing waves inside a column of air. And here they've got some background information telling us that when the wavelength of the standing wave is significantly longer than the diameter of the pipe, and you can see that here, it looks like we've got some kind of antinode here and here. And that distance, which I suppose would be half a wavelength, is definitely greater than the diameter of the pipe. They're telling us that when that's the case, the energy being transferred in and out of those standing waves doesn't radiate particularly efficiently out of the end of the pipe. The other thing that they're telling us is it's a bit of a lie that the end of the pipe is a pressure node. Just a moment ago, we made the argument that because it's open to the atmosphere, the pressure must match at the end. And that was our boundary condition for pressure. Let me repeat, the end of a pipe has to be a pressure node, no fluctuations about atmospheric pressure. Well, evidently, if you do the calculations, the acoustical calculations, which I've never actually seen, the actual location of the node is a little bit beyond the end of the pipe. So we're not going to worry about that distinction, but it's worth noting. And when I say a little bit beyond, the extra distance is significantly less than 1 wavelength or even half a wavelength. Down here, they're showing us that when the wavelength, you can see here the wavelength is shorter. When it's on the order of comparable to the diameter of the pipe, you get more efficient transfer of the energy from within the pipe to outside. And I wouldn't be surprised if the term impedance matching is appropriate here. It's a topic that comes up in various engineering disciplines when you're talking about electromagnetic waves being sent down a transmission line. Anytime the waves have to jump from one medium to another, there could be what's called an impedance mismatch. And you have to match impedances to get the most efficient transfer of power. That's probably what's going on here. This same website has some other simulations. I just clicked on the tab right below open-ended pipe. And these are showing you the richer normal modes which actually exist in a three-dimensional box. So all of the musical instruments aren't really one-dimensional, are they? It's a three-dimensional volume within the trumpet, within the saxophone. If the tube is narrow enough, then the one-dimensional model evidently is perfectly fine to use. It's fairly accurate. But you do want to keep in mind that when you're standing in the shower singing, for instance, those waves can bounce back and forth, side to side, up and down, also at two axes side to. Imagine yourself standing in the shower. They could be oscillating front to back, side to side. Those are both oscillations parallel to the floor and then from floor to ceiling. So it's really a three-dimensional standing wave phenomenon. And we're not going to worry about that in our homework and the exercises that we look at, but it is worth keeping that in mind. And it's totally doable to calculate the normal modes in 3 dimensions. So here it looks like they're showing us some visualizations of those 3-dimensional standing waves. You see, if you go from left to right, you can watch how the pressure changes in time. It looks like, excuse me, the center of the tube looks like a pressure antinode. It's fluctuating with a maximum amplitude. And then right here where I've put the hand pointer, that would be a pressure node. And then there's pressure nodes also at the ends. This must be a closed pipe. Yeah, it's like a closed box. Because remember, if this was open to the atmosphere, then the pressure would have to have a node there. So this must be closed all around. So I just described the location of the pressure antinodes from left to right, but you can also go from bottom to top of the diagram and describe how the amplitude of oscillation of the pressure also depends on that coordinate. And again, they're only showing us the 2-dimensional dependence. You can see they've put n sub z equals 0. So we've just eliminated the dependence on z. These are fun to stare at. If you'd like to see some real representations of 3-dimensional acoustical modes or 3-dimensional standing waves, you can consult the Falstad website because it seems to have everything you could possibly want. It looks 2-dimensional, but check this out. If you click and hold the mouse, you can rotate it. And what are we looking at here? I think the 2 different colors are helping you visualize that the particles of air on the 2 different sides of the cube are probably 180 degrees out of phase. So when these particles are experiencing their pressure slightly higher than equilibrium, the particles down here are experiencing a pressure slightly less than equilibrium. What happens if we click on another one of these boxes? Well, first let me uncheck this box. Aha, no oscillation. And then I'll try a different one. Woo. I like these Christmas colors. You can see there are many more nodes and antinodes there. And if we think of this cube as being closed, then we know that pressure antinodes exist at the walls and displacement nodes exist in the same place. The particles of air, if we're talking about sound waves, cannot jiggle back and forth against the wall because they bump up against it. So those have to be displacement nodes. And the fact that we've got this colorization at the wall means the colors must represent the pressure. If I uncheck that mode, let me try a different one because that was a little crazy. Okay, so the structure of these modes is obviously more complicated now that we've moved to 3 dimensions. Now what happens if I just check several of these? Yikes. Now we've got stuff in motion. And I just can't resist. I have to point out something. Again, one reason to study this stuff is it equips you with all these mental pictures and basic analogies to understand more interesting things like the electrons in atoms. And we're going to see towards the end of the semester that the hydrogen atom, the simplest atom of all, has a set of so-called stationary states in which the electron can exist. So let me uncheck these except for one. If this was the state of the hydrogen or the electron in the hydrogen atom, notice that the distribution, if you think of the colors as the probability distribution of the electron, it tells you where you're more likely to find the electron and where you're not likely to find it, you can see that that probability distribution is constant in time. But when the particle is in a superposition of standing waves, you can see that the colors are flowing around. I don't know how clear that is. Let me try a few more. It's definitely in flux. And that would not be considered a stationary state. And you can show that in a superposition of stationary states, the electron's probability really is flowing from one point to another. And you all know that electrons are charged, electrically charged. They have a negative electrical charge. And if the probability of the electron is moving around in space, then you might think that the charge is also, in some sense, moving around in space. And hopefully you also know from 3B that when you take electric charge and wiggle it back and forth, accelerate it, you emit electromagnetic waves. So when the electron in the atom is in a superposition of states, it may be transitioning from one stationary state to another. And during that transition, its charge is sloshing back and forth and it's emitting light. And we'll have more to say about that towards the end of the semester. Last thing we should do here. What happens if I click Show Spectrum? Well, I don't know how to interpret that. So moving on. Okay, I figured that out. Now, what I don't know is how exactly the modes are ordered here. Can I just refresh? So these modes, it turns out, would depend on 3 indices or indexes. The standing waves that, excuse me, that we're talking about only need 1 integer. Remember the transverse waves on the string? We just used the integer n. We really just counted the number of antinodes, and that's the same number that describes which mode we're talking about. Well, in 3D, you would need 3 integers. You would count how many antinodes there are going from left to right, front to back, and top to bottom. So I don't know how they're ordered on this grid here, but you can see if you zoom in, I can't zoom in, selected mode equals 441. But that probably is the number of antinodes along the various axes. So this one is 231. Can we confirm that? Yeah, it looks like from left to right here, I count 2 pressure antinodes. If I flip this cube around, there's 3. And then if I look at the last, okay, there goes my theory. I think I'm just counting it wrong. I'm probably onto something. So when I clicked Show Spectrum, these vertical lines represent the various possible frequencies of oscillation that can exist for a standing wave. And as I hover over the grid, you can see one of those frequencies gets highlighted in yellow. Each of these grid squares represents a possible standing wave in 3 dimensions that oscillates at a particular frequency. And I think I know why. When I hover only one box, a whole bunch of boxes light up. And it's because those other modes happen to oscillate at the same frequency. So when you move into 3 dimensions, it's possible to have different modes oscillating at the same frequency, and that's called degeneracy. In fact, it's called accidental degeneracy. But now I'm getting away from our own curriculum. I just wanted you to be aware that when you're singing in the shower, the modes you're talking about are really 3-dimensional, and that would even be true for musical instruments. But think of a trumpet, a trombone. You've got a really long tube, a long column of air that's rather skinny. It's probably skinnier than, excuse me, the diameter of the tube is probably less than the wavelength or comparable. So that makes the 1-dimensional model pretty good. Now, while we're here on the Falstad site, I know I titled this presentation Longitudinal Waves, but I can't help but take a little diversion because I should have shown this to you earlier. Let's go into the circular membrane waves applet. Membrane, gross word. So what we're looking at here are transverse oscillations on a thin membrane. So instead of a string, which is 1-dimensional, we've got this membrane, basically a circular flexible disc, and the particles within the disc are free to oscillate perpendicular to the membrane. In other words, transverse to the membrane. And it looks like this is the fundamental mode of vibration for a circular membrane. It might be easier to visualize if we switch from the solid view to the wireframe view. I kind of like this better. Okay, what does the next mode look like? Cool. Instead of one antinode, which you saw in the first mode, we've got two antinodes. And these would be displacement antinodes if we're actually talking about, up and down oscillations of a drum head, for instance. You could think of this as the head of a drum. What about one of these higher order modes? That's pretty complicated. Now, which of these are actually excited when you, let's say, strike a snare drum with the drumstick? Probably a bunch of them simultaneously. If you think about it, when you hit a snare drum, you don't hear a pure tone. You kind of hear a percussive noise, and noise is a whole bunch of frequencies. So that's my guess. When you strike a drum, you're hearing a lot of these modes simultaneously excited. How crazy can we get here? That's just too chaotic. Pretty neat. Show frequencies. Okay. What happens if we increase the resolution? It runs a little slower, but it looks better too. How about the brightness? Oh, can't do anything with the brightness. Okay. How about we go back and check out a rectangular membrane fundamental mode? Also, did you notice that the higher modes generally had higher frequencies? So if I go to this one, I'm expecting it to oscillate more quickly. Yep. What just happened there? Oh, I've plucked the membrane and okay, my browser's running a little bit slowly, but do you notice how right now I've got the mouse set to poke the membrane? Let's go with the strike membrane. This is just getting grosser and grosser. Wow. Speaking of hitting a snare drum, let's go back and do that with the circular membrane. Does it have that option? Membrane. Can I use the mouse to strike the membrane? Yes, I can. Okay, here goes. Falstad answered our question. Evidently, that's what happens when you strike a drum head. Now, eventually, the oscillations will be damped out. See how it says damping right here, and the slider is set to 0? Let's put some damping in there and watch out. After a short amount of time, the whole thing stops oscillating. Okay, maybe a not so short amount of time. If I turn the damping up, sure taking a while here. Okay, I'll let you play with this. Endless hours of fun here, or at least minutes of fun, right? Before you get bored. If the computer simulations are not compelling enough for you, let's take a look at some real standing waves on two-dimensional plates. This demonstration is called Kolodny Plates. I think I'm pronouncing that correctly. I've never actually heard somebody say this word out loud. Kolodny. I don't think it's Chaladny. And the sound that you're going to hear here is a little hideous, so you might want to turn your volume down. Here I go. So what you're seeing there is this guy successfully exciting one or more of the normal modes of this circular disc. That's probably salt. And if you had to guess, would salt collect at antinodes or nodes? Well, the antinodes are oscillating up and down with the greatest amplitude, I think the salt would be kicked away from the antinodes. So we're probably looking at the nodes. That's like the valleys. Well, I shouldn't say the valleys, because valley is like the opposite of a peak. We're looking at the places where the plate is not oscillating up and down. And by moving the bow to a different position and perhaps bowing it with more strength, I don't know exactly what he's doing, but then he's managing to excite a higher harmonic. So I'll let you peruse these at your leisure if you're more interested, but I'll remind you that we're looking at normal modes for transverse oscillations on a two-dimensional structure. Okay, one more, because this one's so cool. You can find lots of videos of these on YouTube. Some people have done larger versions. I found one guy who used couscous instead of salt. You can even examine the possible Kolodny patterns on something shaped like a violin. Again, watch your volume here. So if you've never thought about it before, when a violinist is playing, there are going to be certain frequencies, certain strings with the bow drawn across certain parts of the string that will set the body of the violin into normal mode oscillation like this. How cool would it be if you had normal mode vision? So if you go see a symphony orchestra play, and not only can you hear the sounds coming out of the instruments, but you could see the violins and the cellos oscillating in their normal modes. Okay, time to move on to longitudinal standing waves, since that is, after all, the title of this presentation. Here's a famous demonstration, or popular demonstration, called Kuntz tube, I think it's pronounced. And the demonstrator here in a moment is going to turn on an electronic oscillator that forces this speaker to wiggle back and forth many times per second. And that's going to set up longitudinal waves in the column of air inside this tube. And then these are probably polystyrene, I don't know. I don't know anything about chemistry. I saw this word somewhere in one of these videos. They're very lightweight little balls, kind of like styrofoam. And they're light enough that the pressure oscillations in the air can move those styrofoam balls around. And you'll notice that they collect in some places and they avoid other places. Those must be the pressure nodes and antinodes, or maybe I should say the displacement nodes and antinodes. So I would imagine that as the air is jiggling back and forth, these styrofoam balls are going to collect at the displacement nodes, because that's where they won't be kicked back and forth. And they're going to, am I getting that right? Yeah, maybe you have a better explanation. But before I hit play here, please note that you'll see a large scale pattern of nodes and antinodes, but then within the antinodes, you'll also see smaller ripples in the accumulation of the styrofoam balls. And I think that's because the speaker is not really putting out one pure tone. There's probably some higher frequencies mixed in there that can't be avoided. And so you've got like another standing wave at a higher frequency. That's my theory. The volume here is loud, so watch out. Here I go. what are we looking at here? You can see, it's interesting. This demonstration almost allows you to, sorry, I've got the demonstrator in an awkward position. You can almost see that schematic representation used in the diagrams. We're really looking at a standing wave where the air particles oscillate back and forth, but then these styrofoam balls stack up so that you can see that transverse outline. It's kind of an unintended benefit here. So the styrofoam balls, my thinking is they're going to be kicked away from, maybe this would actually be a displacement node. If this is a pressure or a displacement antinode, wouldn't that be kicking the styrofoam balls away from it and they would accumulate at the displacement antinodes? Like I said, maybe you've got a better theory. I couldn't resist using one of our formulas to check the result here. Remember the fundamental relationship for waves? Speed of a wave is equal to the product of wavelength and frequency. Well, here in the picture, we can basically see the wavelength, because whether this is a displacement node or antinode, I still have to figure that out. Clearly, this is a node, this is a node, and this is a node. And we know that the the distance between two nodes is a half wavelength. That's one hump, which is a half wavelength. So the full wavelength would be from here to here. Now, if I had to guess, I would say this is around 1.5 meters. It looks longer than a meter stick, but not as long as 2 meters. We know that the speed of sound in room temperature air is 343 meters per second. So let me just take that 343 on my calculator. I'm dividing that by the given frequency of 238. And I find that the wavelength would be 1.44 meters, which is pretty close to my guess. This one's even louder, so you'll definitely want to turn your volume down or just take your earphones out altogether here, earbuds. It doesn't get any clearer than that, does it, as far as the demonstrations go? I'm thinking that where the styrofoam balls accumulate would have to be a displacement node, because the air particles in between there would be moving back and forth, and it seems like they would tend to kick the balls away from that area. Okay, I don't know about you, but I'm pretty solidly convinced that there are standing waves in air in a situation such as this. What would make the Kunst tube demonstration even cooler? Well, the answer is applicable in a lot of other situations too. Fire. So this is called a Rubens tube. This one seems to be more popular on YouTube for obvious reasons. This time, instead of regular old air, which is mostly nitrogen, as the medium inside the tube, now he's pumping propane. I assume it's propane. And there's a bunch of holes poked in the top of the tube through which flames can appear. And if you think about the pressure standing wave, wherever there's a pressure antinode, you've got greater fluctuations of the gas pressure. I'll be honest, I don't actually know if the flames are going to be higher at the nodes or the antinodes. Maybe this guy will explain it to us. But the height of the flames will show you very clearly that there's alternating nodes and antinodes. Volume warning again. Okay, now if we take his language literally here, the low and high flames reveal, respectively, the unseen nodes and antinodes of the standing wave. Well, he's not specifying whether that's a displacement node or pressure node. If you've got a compelling theory, email it to me. In the video we were just watching, the frequency generator was putting out pure tones, single frequency tones. And that's why we saw that nice sine wave in space, that periodic wave. Well, if you pump music through the gas inside the tube, music consists of a whole bunch of frequencies, and the frequency content is changing all the time. So obviously you're going to get a more complicated pattern of high and low flames like this.
It's the eye of the tiger, it's the thrill of the fight. It's rising up from my life.
Okay, that's enough fun for now. Let's use our brains now and investigate the reason for the relationship between the location of displacement nodes and the location of pressure antinodes. Here's a graphic from your book describing the change in time of the positions of a string of particles here. And the graph here shows the displacement of each of those particles from equilibrium at t equals 0 seconds. So when the clock starts, this is what the particles are doing. Just a moment prior, they were undisturbed. So it's sometime between this time and t equals 0 is when this pulse arrived. This pulse is moving to the right, so this is not a standing wave. This entire waveform would be translating to the right in time because this is a snapshot graph. And it takes a little bit of thought to see how this graph explains this configuration of all the particles. So let's just start from the left. Let's look at the particle, excuse me, located at x equals 0 centimeters. So the particle hanging out at the origin. Its displacement at this time, t equals 0, is 0 seconds. That's why the height of the curve here is 0. Remember, the vertical height of this curve actually tells us the displacement left or right of the particle located at that position. Right now I'm talking about the particle here. Now the particle, which normally hangs out at x equals 1 centimeters, evidently has been displaced to the right. Remember, a y-coordinate on the graph that's positive corresponds to a displacement to the right. And I can interpolate here and see that that displacement is about 0.5 centimeters. So that's why this particle is shown scooted to the right by half a centimeter at t equals 0 seconds. What about the particle located at 2 centimeters? Well, when I say located at 2 centimeters, that's its equilibrium position, but at this time, it's presently displaced by 1 full centimeter to the right, as we can see here. So normally this particle would be hanging out over here, but it's been pushed all the way over to x equals 3 centimeters actually, right? Normally it's at 2 centimeters, it's been pushed all the way over to 3 centimeters. Okay, what about the particle which normally hangs out at 3 centimeters? It's been pushed half a centimeter to the right, and we can see that right here. And finally, the particle which normally chills at 4 centimeters is not displaced at all because the height of the displacement function is 0 there. So it's still at its normal equilibrium position. Then we go past that. Each of these particles in here has a negative displacement. So let's look at the particle which is normally at 6 centimeters. It has a displacement of -1 on the graph. That tells us that it's been scooted to the left. And this is the important point. Do you see how all these particles are bunched up? You could say that the density of the fluid is higher there. That's a compression. And you see that that happens when going from left to right on the displacement graph, the displacements go from positive to negative. See that negative slope there? Anytime the displacements are going from positive to negative on the displacement versus position graph, you end up with this compression. Now, it's unfortunate that this particular graph doesn't have the curve continuing on upwards here. It would be nice to see what happens if the displacement goes from negative to positive. In other words, a positive slope. Because then you can sort of see it here. Since these particles have been pushed left and these are just hanging out in their normal position, you get a bit of a rarefaction here. That's the opposite of a compression. And the density of the fluid would be a little lower there, as well as the pressure. It would be even more pronounced if each of these particles had a positive displacement at this time, t equals 0 seconds, and then all of these would be pushed to the right, and you would really see that rarefaction. So just to summarize the rule, when the displacement versus position goes from positive to negative, in other words, when it has a negative slope, you get a compression, and that means higher pressure. When the displacement goes from negative to positive, in other words, a positive slope that passes through the x-axis, you get a rarefaction. And then, of course, that whole pattern is moving to the right, and they're showing you what happens 1 second later and 2 seconds later. That disturbance is traveling to the right. This is not a standing wave. This is just a single pulse traveling down this fluid. Here's a screenshot from Dan Russell's site, and this was taken from the animation of an actual standing wave. So just looking at this graph of displacement versus position, yeah, the axes aren't labeled here, but this graph shows you displacement versus position along the tube. So the particles right here evidently have a positive displacement, which means they've all been pushed to the right, away from their equilibrium positions. These particles here have a negative displacement. That means if they normally hang out here, they've been pushed to the left. So this shows you how the displacement, the wiggle left and right, depends on where you are in the tube. Same thing for the pressure wave down here. And we can confirm the behavior I just described in the previous slide. So right here, we've got the displacements going from positive to negative. So all these particles have been shoved to the right, away from their equilibrium positions, and all these particles right here have been shoved to the left. That's why they all bunch up, and you get a higher pressure right there. And you have to imagine, see the dotted line here is showing you that if you then play this animation, this peak is going down to a valley and back up. So this is a standing wave. You don't want to picture this whole waveform traveling to the right because it's not. The antinodes are flipping up and down. It's a standing wave. Here we can actually confirm the opposite behavior. So we've got the displacement going from negative to positive. So these particles have all been shoved to the left at the current moment in time, and the particles right over here, according to the graph, have been shoved to the right. And that's why they're spread out. And the pressure for a moment is less than it normally would be. Okay? So hopefully that makes it clear the reason for the relationship between a displacement node and a pressure antinode. Same thing over here. This is a displacement node and a pressure antinode. So right now, at this moment in time, there's a rarefaction at this location in the tube. But half a period later, this black curve will have moved to where the dashed curve is, and will have the opposite slope, and so that rarefaction will become a compression. And that's why the pressure a half period later will be up here. But you can see that the nodes and antinodes are offset by half a wavelength, it looks like. Is it half a wavelength or a quarter wavelength? Here's an antinode for pressure. Here's an antinode for... Okay, that's 1/4 wavelength. I guess that's a rule worth memorizing. To move from the pattern of nodes and antinodes for displacement to the pattern of nodes and antinodes for pressure, you scoot over by 1/4 wavelength. Now, how does one go about establishing a standing longitudinal wave in a column of air, for instance? Before we say a word about that, let's revisit pulses traveling down strings. Remember these two simple boundary conditions? If you have a pulse on a string approaching a hard boundary, that's what we called earlier a fixed end, the pulse gets inverted before it reflects, or I should say it gets inverted upon reflection, whereas a loose end doesn't create an inversion. The pulse is inverted and it's still right side up. It's also worth noting, it doesn't have to be one of those two cases. It could be a wave traveling along a string where it encounters a change in density. Think of this as two strings of different densities tied together, or some other means of joining them together. I say that because if there's a knot between the two, that probably complicates things. You can see even a change of density causes a reflection of the incoming pulse as well as a transmission. Look at the amplitude of the incoming pulse here, and you'll see that upon reflection, the amplitude is reduced. It's also inverted. So some of the incident energy is reflected, some of it is transmitted, and there's also what we would call a phase change. That's the reflection. That's the inversion. An inversion corresponds to a phase change of pi radians. Down here, you've got a wave on a heavier string encountering a lighter string, and you see that there's no inversion, but there's still reflection and transmission. And this is probably the first time you're encountering that type of behavior, but many of you will see it again, depending on which classes you take in the future. If you're going to major in electrical engineering, you'll definitely encounter analogous behavior for electromagnetic waves traveling from one medium to another. There's a certain amount of energy that's reflected, some that's transmitted. For instance, when you bounce light off of glass, if the light is incident normally, that means perpendicular to the glass, then something like 4% of the intensity is reflected and the rest is transmitted. And that 4% that's reflected is what allows you to see your image in a storefront window during the day. If you're walking down the street, back before COVID and lockdown, you can see yourself in the reflection from a storefront window. That's because of that partial reflection. And the behavior of those light waves is very analogous to what you see here. You even see it in quantum mechanics when you talk about a wave representing the probability density of a particle. And when that wave encounters a difference in potential energy, you get partial transmission, partial reflection. I keep hammering home this point. There's a lot of good reasons to learn this stuff beyond just the intrinsic interest that it has, sound waves, waves on strings. These ideas apply to other more interesting, more abstract concepts. What about a wave train? So instead of a single pulse, a sinusoidal train of pulses. Let's start this over. Refresh. Okay, it's not working. There it goes. Okay, did you notice what happened? It started out with just a single traveling wave to the right. I'm trying to get this to start over. Here we go. This is one progressive wave traveling to the right. After reflection, we now have a standing wave. So if you can just establish one wave, if you have some driving force on one end, sending a traveling wave forward, if there's any kind of change in the change in the medium or a impedance mismatch, I'm using that term loosely, but you'll probably hear that in the future, then you get a reflected wave, and the incident and reflected waves set up that standing wave. The same thing is true for longitudinal waves. Let me try refreshing this. I think it's just going to reset. So this is a single pulse, it looks like. Yeah. But as this pulse travels down and reaches the closed end of the tube, there will be a reflection. And you may notice that I think the pressure pulse was not inverted. Let's see that again. So for a closed end, what happens to the leading edge here is on top, and after it reflects, the leading edge is still on top. So no inversion, or you could say no phase shift of pi radians when you're talking about the pressure pulse for a closed end. For an open end, it looks like there is an inversion. And that rule is stated right here. Pressure is inverted upon reflection. Now, we're not going to need that fact. How would you prove that? You're going to need some physics beyond what's described in our book. But the takeaway here is that a single traveling wave down a tube, when it, excuse me, when it encounters an open end, some kind of change in the medium, there tends to be a reflection. And that's all you really need to set up these standing waves. And the reason we care about this is if we're talking about a trumpet, for instance, think of the right end here as the bell of the trumpet where the sound comes out. And over here on the left end is where the mouthpiece is. So the person's lips are buzzing in the mouthpiece, creating traveling waves that go down to the other end. Well, how do you get those standing waves? It's one thing to send traveling waves one direction, but we know that a standing wave involves waves going to the left and the right. That happens because of the reflection. Steve Spangler has a great demonstration for us here.
Great science experiment from our demo archive. You heard of the genie in the bottle? You know, you find the bottle, uncork it, genie comes out. Well, this isn't as classy. It's called the genie in the tube. Genie in the steel pipe, whatever. And the only way to get the genie out, you can come out, genie, see, it doesn't work. The only way you can get the genie out is with fire. Now, already some of you like this demonstration even more than you thought you were going to like it. So here's what we're going to do is that you simply wake up the genie. Oh, great genie, come out of the tube. All right, here we go. We're working hard to get the genie out of the tube. Wake up, genie, wake up, wake up, wake up. Let's see if the genie... Do you hear the genie? Perfect. So that is the dumb genie. All right, so you can actually pour the genie out and put the genie into the cup like this, or you can pour the genie back in. All right. Okay, stop. There's not a genie in the tube. Of course, there's not a genie in the tube, but it is a great, isn't that crazy? A great discrepant event that the sound comes out of the tube. No camera tricks, no, I'm now tired of that. No camera tricks, nothing like that. The sound that you're hearing, we didn't dub over. So you're really making sound come out of the tube, and how does it work? Well, the reveal is pretty cool. I have a glass tube, a furnace tube that I'm using that will show you the secret. If you take a look at this right here, there's a piece of screen. Now, it's a heavy gauge metal screen. So what we're really doing, and since I'm using glass and this thick pipe here I can hang onto with no problem at all, but the glass tube heats up fairly quickly. So for that reason, I'm going to throw on the glove. All right, so I'm going to hold on to it like this. Watch what happens when we heat up the tube, or when we heat up the screen inside. So here's our flame. There it goes. Look at this. Nice. There it is. So you have now the great conductor of heat right down here, and that's now the hot air rising, correct? And we have air being pulled in through the pipe, resonating in the tube, right? And you hear that sound coming out. So putting my hand over the top, that's why it stopped it.
Okay, if we'd like to add a little nuance to that explanation, here's what I would say. Can I back up a few seconds? Once this piece of metal gets really hot, then the air directly above it gets very hot, and that means the air expands, it gets less dense. We know that less dense air rises, or you could just say warm air rises. And as that air flows down the tube and over the top lip of the tube, it's probably going to excite all kinds of frequencies of vibration. Maybe there's turbulent flow within the tube. Just think of there being a broad spectrum of noise within the tube, lots of frequencies, and all of them to some extent are going to be reflected at the end of the tube. But we know that in general, and I'll go back to the FET transverse wave on a string simulation. If you just shake a rope at random frequencies, a rope that's fixed at one end, you are going to get reflection, but the reflected wave will interfere with the incoming wave in such a way for most frequencies that you get a unorganized combination of constructive and destructive interference. You get interference in any case, but it's only when the frequency corresponds to a wavelength that fits into the length of the medium, that you get a standing wave, right? There's only a discrete set of allowable frequencies when we're talking about standing waves. So it's only those frequencies which reinforce themselves, so to speak, after reflection and make a standing wave. And the tone that you're hearing comes from that particular mode. So again, the flow of that hot air is going to, it will be associated with all sorts of frequencies flowing down the tube and then reflecting, but it's only the so-called resonant frequencies, in other words, these harmonics, which reinforce themselves and produce an audible tone. Here we are back in the FET wave on a string simulator. The right end is fixed. Think of this wrench, which is about to oscillate up and down, as being like the hot metal screen, or just that temperature gradient, which is producing those waves that travel down. And you see immediately that you do get reflection, but you don't really get a standing wave because the frequency isn't quite right. Now, whatever frequency this is, if we knew where an antinode should be, we could put the oscillator at that position. But this oscillator, the driver here, I should call it, is evidently not located at an antinode. And that's why we're not able to see standing waves here. If I change the frequency, maybe I can get something that looks even more disorganized. Yeah, this wave is not really reinforcing itself upon reflection. It still looks like it's mostly traveling to the right. If we were getting the kind of interference characteristic of a standing wave, then you would see a standing wave. The nodes and antinodes would be standing in place. Now, again, I don't know how to pick the right frequency here to actually set up a standing wave, but if I were successful in doing so, that would represent the particular sound waves that upon reflection do set up standing waves, and that's the tone that you heard coming out of the singing tube. Okay, I fiddled around with this for a bit, and I actually found a frequency that was working pretty well. This looks like more of a standing wave than previously. So this particular frequency, 1.84, upon reflection, interferes with itself in such a way that you get that characteristic pattern of constructive interference at the antinodes and destructive interference at the nodes. It doesn't hold forever, right? If you watch this long enough, the standing wave seems to disappear, but then it comes back. That singing tube is a lot like an organ pipe. I think this is called an open flue organ pipe. And the idea is a bellows, some means of forcing air, forces air to pass through this flue. And in so doing, it creates turbulence. You know, there's laminar flow and turbulent flow. Instead of a nice, neat, streamlined motion of the air through this channel here, it probably swirls around and there's vibrations. And so it creates noise. It sets up a whole range of frequencies that travel down the pipe. Again, many of them or all of them reflect to an extent at the end, but it's only certain frequencies, that reflect and interfere with themselves in such a way as to set up standing waves. And it's not only one mode that does that. I've mentioned that all musical instruments, unlike tuning forks, when you play a single note on that instrument, you're actually hearing a whole set of frequencies. You're hearing not just the fundamental frequency, but a set of harmonics. And their relative weights give the instrument its characteristic timbre. One of those tends to dominate. I guess that would be the fundamental. That's what you think you're hearing, but you're really hearing a set of harmonics. So here's a graph I pulled up of the spectrum of sound coming from an organ pipe. And the height of the bars gives you the relative amplitude of those various harmonics. Clearly, the fundamental has the highest decibel level. And that's why you tend to feel like you're hearing one note. But the frequency content is more complicated than just that. So each of these bars correspond to frequencies for which you get constructive interference at antinodes and perfect destructive interference at nodes. Most of our work here is actually done already. let's lastly just develop the formulas that we need to calculate the various harmonics for tubes that are closed on both ends, closed on one end, open at the other, or open at both ends. So we'll start with the closed tube. And I'm not aware of any musical instrument that's closed on both ends. I don't know how you would play such an instrument. But remember, the particles at the closed ends are not free to oscillate back and forth. They're constrained by the closed end. So those must be displacement nodes. And we know that displacement nodes are the same locations as pressure antinodes. Now, what is the lowest frequency that we can have inside a closed tube? Lowest frequency corresponds to the longest wavelength. So you've got the pressure picture and the displacement picture drawn on top of each other here. However you look at it, you know, if you think about pressure first, we know that for a closed end, we've got a pressure antinode because the particles are going to bunch up there and then spread out and bunch up every half period. And you get this picture, right? There's no way you could make, like, see this first part that I'm tracing out? You can't stretch that out to cover the whole length of the pipe, because if you did, this pressure node would be at the end of the pipe, and that would mean a displacement antinode would have to be there, because pressure nodes and displacement antinodes happen at the same place. But this can't be a displacement antinode. Get the picture? So this is how you must draw the picture for the lowest harmonic, or the fundamental. If you want to cram another wavelength in there, or half wavelength, let's see here. How many wavelengths do we actually have here? This is one hump, right? One hump is half a wavelength. Okay, so this is different from what I was describing earlier in the presentation, where we had a closed open pipe. This is closed. Okay, so half a wavelength. And then this next one we can draw, keeping in mind the boundary conditions. We've got a quarter, another quarter, another quarter, another quarter. In other words, a half wavelength plus a half. Well, that's a full wavelength, right? You can also see that by looking at the blue. This is two humps, or a full wavelength. So half a wavelength, two halves wavelengths. That's the same as one wavelength. And here I count 1, 2, 3 half wavelengths. I think we've done enough to establish a pattern. It's pretty clear. And this looks familiar. The length of the pipe must be an integer number, really a natural number, starting with n equals 1, 2, 3, etc. An integer number of half wavelengths. You could solve this for lambda. Haven't we seen this before? This is identical to the requirement for standing waves on a string, standing transverse waves. We've already seen these formulas. And that means everything that follows will also be applicable to standing waves in a closed pipe. So I'm quoting the result here. Actually, this is just a fundamental relation for waves, right? The relation between frequency, wavelength, and speed. If we combine these two results, we can write it this way. And here's where I say, hey, set n equal to 1, and this expression v over 2L, that's going to show up in the frequency formula for all the modes. Let's just separate that and call it F1. So F1 is what you get when you evaluate this for n equals 1. You've seen this before. And that's great. That means you don't have to memorize a new formula or put a new formula on your note card. The only thing that's different, of course, is the formula for the speed, because we're not talking about transverse waves on strings. It's not enough to talk about string tension and linear mass density. Now we're talking about the bulk modulus and the volume mass density. If you'd like to see where this formula comes from, your book also derives the wave equation for longitudinal waves in a fluid, like air or water. Another guy with a mustache here, singing in the shower. Well, I pointed out a while back in this presentation that it's not really valid to think of a shower as a long, narrow tube of air. So the one-dimensional model is not really sufficient. You'd have to go back and look at the three-dimensional acoustic modes for a box, like I showed you on the Falstad website. So here's another visualization of some of those modes. And I think this one in particular, is it this one? Yeah, if you think of this as the ceiling, the top of the shower, and this is the bottom, these colors might show you where the, let's see, that would be the pressure, no, that would be the displacement antinode, right? The particles in the middle of the shower, like halfway up from the floor to the ceiling, they're free to oscillate with large amplitude, but there has to be a displacement node at the ceiling and the floor. So this might be the first fundamental mode of oscillation for three-dimensional acoustic vibrations. And there's a whole set of those frequencies that can exist in the shower. They tend to resonate, and that's why you sound good when you sing in the shower. Some of us more than others. I'm using some fancy language now here. Let's call this the resonance spectrum of a closed tube. I may have at some point in these last couple presentations said, oh, these are the only frequencies that can exist within a column of air. That's not really true because, as I mentioned, the mouthpiece of a trumpet produces a broad spectrum of noise, you could say. All those frequencies are going to travel down the tube, but only these frequencies will reflect in such a way that, or reflect and interfere in such a way that they set up standing waves. So it's not really correct to say that no other frequencies can exist. They're just not going to resonate. So it makes sense to call this the resonance spectrum of a closed tube. And just like before, each of these frequencies we've seen is an integer multiple of the fundamental frequency, which means you can represent them as a ladder with these equally spaced rungs. And here's everything combined into one formula where you can calculate, well, I guess two formulas, right? F1 is expressed in terms of the length of the tube, the bulk modulus of the fluid, whether it's air or water, and the volume mass density, kilograms per cubic meter. Okay, let's move on now and do an open tube like a flute. It's not totally obvious, but one end is certainly open, and this may not be the actual end of the flute, but it's the end of the effective length of air that's free to vibrate. You know, right here, it's open to the atmosphere, so you would have that boundary condition. The pressure at the mouthpiece would have to be equal to atmospheric pressure. And the picture says everything we need to know. Let's talk about pressure because both boundary conditions involve the pressure. The pressure has to have a node at both open ends because the pressure must match at all times atmospheric pressure. That means no fluctuation above and below atmospheric pressure. So if it's a pressure node, it must be a displacement antinode. You can go through the pictures and convince yourself that the formula ends up being the same because how many wavelengths are we looking at? Previously, the blue one was easy to see. Now it's the purple one here. That's half a wavelength. This is 2 half wavelengths. Down here for the third mode, we've got 1, 2, 3 half wavelengths. The length of the tube must be an integer number of half wavelengths. Everything's exactly the same. Okay, so the set of frequencies that resonate for an open tube are identical to a closed tube. There's no extra formula to memorize. Okay, closed, open, same thing as far as the frequencies go. So we can modify this slightly and call it the resonance spectrum of a closed or open tube. And the last thing to do here would be to look at the spectrum of an open closed tube, which also describes a lot of musical instruments. The last case that we have to look at is one that we touched on earlier in the video, and that's the open closed tube, which is a good model for a lot of musical instruments as well. Case in point, the clarinet. The player seals their lips around the reed, so the left end here would be closed, and this, of course, is the open end. Okay, so we can move more quickly because we've already talked about this. Look at the pictures and you can sort out the fact that the fundamental mode consists of a quarter wavelength, not a half wavelength. The next higher mode, or the second harmonic, actually your book chooses to call this the third harmonic, is the one with, count them, 1, 2, 3 quarter wavelengths. I've put these dashed lines there to help you see that. And this slide from your book is using the letter M instead of N. So 1 quarter wavelength, 3 quarter wavelengths. This one down here has 5 quarter wavelengths. I think that's enough to establish a pattern. The length of the tube must be an integer number of quarter wavelengths. That's the condition for resonance. Solve that for lambda and you get this. It looks familiar. The only difference is the 2 here has become a 4. Don't forget the fundamental relation for waves. That's the relation between frequency, wave speed, and wavelength. That's always true. And take this formula for lambda, plug it in here, and you get this formula, which also looks familiar because we saw this before for standing waves on strings and standing longitudinal waves in closed tubes and open tubes. The only difference is the 2 has become a 4, and I guess there's 2 differences. The integer n has to be odd. Okay, so we can summarize by saying all of the harmonics for an open-closed tube are multiples of the fundamental, but this time the fundamental is not v over 2L, it's v over 4L, and it must be an odd integer multiple. So let's do a side-by-side comparison. This will make it easy to remember all the formulas. For an open-closed tube, we've got the 4 in the denominator instead of the 2, and the multiples must be odd. Let me say one more thing. When we're talking about the harmonics and naming them, at least according to Dan Russell's page, the convention would be to call this the 3rd harmonic and the 5th harmonic. So I suppose you could say 1st mode, 2nd mode, 3rd mode. If you want to use that word harmonic, let's go with the actual number of antinodes, it looks like. That's another way to think about it. We're still naming the harmonic based on the number of antinodes. When you arrange the frequencies in a column like this, so 1 times the fundamental, 2 times the fundamental, and when I say the fundamental, currently I'm talking about the fundamental frequency for open, and closed. Over here we've got odd multiples of the fundamental, and the fundamental here is v over 4L, 3 times that, 5 times that, etc. Well, check this out. Let's take this 4 and break it up. We can write 4 as 1/2 of 1/2. That's the same thing, right? 2 factors of 2 in the denominator is the same as a 4 in the denominator. And now we recognize that this is actually the fundamental for an open tube. So the fundamental frequency for an open-closed tube is 1/2 the fundamental frequency for an open tube. And we can continue that pattern or that recognition all the way down. 3/4 could be written as 3/2 times 1/2. So actually all of the frequencies of the resonant frequencies for an open-closed tube are what you might call half-integer multiples of the fundamental frequency for an open tube. And that just helps you organize all of these spectra more easily in your head. So here we've got whole integer multiples of v over 2L. Over here we have half-integer multiples of v over 2L. Half-integer just means a number halfway between 2 integers. And if we go back to the ladder diagram, it's very easy to represent this way. So the spacing of the rungs is the same. Maybe it doesn't look that way in my slide here, but these are supposed to all be equally spaced. It's just that the entire ladder has been shifted down by half a rung, so to speak. And that rung spacing it's numerically equal to v over 2L. So the fundamental frequency for open, and closed, that is the spacing between the rungs for either set of frequencies.
Well, that about does her. Wraps her all up.